start by asking you to copy this down, or at least note that on your textbook. It is actually on page. Where is that? That's on page 786. So note that on your textbook. I would like that to be handy for you during your tests, okay, including your final. Okay, there's one more expansion that I have not done. It's called binomial series expansion, or simply binomial expansion. And we have done this with the positive integers. Let's see, for example, what I mean by binomial series expansion. We have known from the pre-calculus math 260. I know this because I'm currently teaching 260. And yesterday I thought about this binomial series expansion. That if I have a plus b, for example, squared, this is a squared plus 2ab plus b squared. And then a plus b cubed, this is a cube plus 3a squared b plus 3ab squared plus b cubed. And let me go a bit further. So to the power of 4, the expansion will be a to the 4 plus 4a cubed b plus 6a squared b squared plus 4ab cubed plus b to the 4th, and so on and so forth. Notice that the coefficient 1 to 1 for a plus b squared, the coefficient 1, 3, 3, 1 for cube, 1, 4, 6, 4, 1 for b to a plus b to the 4th, and that follows the following Pascal triangle: 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, which we get from adding the previous middle two terms. Okay, so if I go to the 4th, it will be 1, 4, 6, 4, 1. Okay, and you can keep on going. So if the exponent is a small integer, 2, 3, 4, or maybe 5, if you want to go one more step, you can just use that Pascal triangle. Now the thing is, what happens if the exponent is a lot higher? Let's say, suppose I have a plus b to the power of 20, and I want to know, find the term with b to the 7th, for example. Then find the term with b to the 7th, then it must be something a to what power b to the 7th. Now, can anybody tell me what is the exponent for a if b is to the power of 7? Nobody knows. Okay, the exponent has to be total of 20. Okay, so for example, if this degree of 4 here, notice that every terms, the total exponent is 4. Right? Okay, again, that's from pre-calculus though. And then likewise here, because this is to the power of 20, if b is to the power of 7, then the a must be to the power of 13. Now, the problem is What is this guy here? What is the coefficient? The coefficient will be 20 combination 7. Or we can also write it as using parentheses, that's 20 combination 7. This is the older way of writing it. This is the older way of writing combination, but this is the one used by our textbook. Older notation, but still used. Okay, now if you want to use your compute 20 combination 7 using your calculator, you can do the following. Let me show you my calculator here. Give me a second. Suppose I want to compute that 20 combination 7. I go to 20. Now for combination, I go to Math, PRB, NCR. So 20 combination 7, and then enter. Okay. I don't think you use TI-84 though. I don't think you use TI-84. So suppose you use TI-30, for example. So if you use TI-30, so hold on, let me write it down first. What did I get earlier? 77520. That's 77520. A to the 13th, B to the 7th. Now, if you want to use your calculator TI-30, suppose you use TI-30, then you will punch 20 first, and then look for PRB, and then move your cursor to NCR, and then after that you punch 7, and then enter. Okay. Now, if you are in my stats class or my pre-calculus class, I will teach you this way. Yeah, if you are in my stats class or my pre-calculus class, I will teach you this way. Now, the thing is, with you, I need to go a bit lower, a bit more fundamental method. That is that definition of NCR is actually equals to n factorial over r factorial n minus r factorial. That's what it means. Okay. So if I have 20 combination 7, if I have 20 combination 7, then it will be 20 factorial over 7 factorial, 13 factorial. Okay. But even this is actually not as complicated as what you may think though. Let me do a small number first. Let me do small numbers first before I go back there. Suppose, for example, I have 5 combination 2. What does 5 combination 2 means? That's 5 factorial over 2 factorial, 3 factorial. Which, if I expand, it gives me 5 times 4 times 3 times 2 times 1 over 2 times 1 times 3, 1. Notice that this part gets cancelled. That part gets cancelled. So we can say the following. If I have 5 combination 2, What it means is I start from 5. Okay, and the 2 here represent 2 factors on the top and at the bottom. 2 factors on the top and at the bottom. Okay, 2 factors on the top and at the bottom. Suppose another example, then suppose I have 10 combination 4. Then what it means? On the top, I start from 10. 10 times 9 times 8 times 7. I need 4 factors. And at the bottom, I start from 4, go down to 1. 4, 3, 2, 1. Of course, 10 combination 4 is something you can use calculator, okay? Don't get me wrong. But later on, we are anticipating the situation where the n is not an integer or maybe a negative number. Okay, then what do we do? And we need to know how to compute that by hand, because I think our calculator cannot handle that anymore. Now then, I think to do this, I will cancel the 8 for this. Okay, and then for the 9, I cancel, I get 3 here. So this is 10 combination 4 will be 210. Then how do we compute, going back, how do we compute 20 combination 7? Then on the top, I start from 20. I get 7 factors down. Okay, 7 factors. And on the denominator, I start from 7 going down to 1. And then start canceling as much as possible. For example, I think I will cancel, which one? 14, I can cancel 14 against 7 and 2. Okay, and what else? 15 against 5 and 3. Okay, and then 16 against 4. That gives me 4 here.
See, Joe, that's why your parents told you not to jump on the bed.
And then 18 against 6, I get 3 here. So the product is the same to 20 times 19 times 3 times 17 times 4. Whatever that is. But if you compute that using calculator, then it will be, I believe that will be the number we get up there, 7,000 something, 77,000 something. Okay, let me try. Go back to my calculator. What's that? 20 times 19 times 3 times 17 times 4. Right? The same? Okay. Now, of course, if you have 20 combination 7, just use your calculator function for that combination. Now, the thing is, we will expand this again. The reason I teach you this because we will expand it later. Okay, we will expand that later. You can see that what we learned using Pascal triangle still apply. Let's say, for example, this guy here, this 6 is actually 4 combination 2. Okay, that's 4 combination 2. 4 coming from the exponent. Okay, and then the 2 comes from the exponent of b. Maybe I use this here. The exponent of b, and this 4 coming from the exponent there. Okay, so this is a fast review from Math 260, Chapter 13. I think that's 13.2. So if you still have your pre-calculus textbook, pre-calculus or pre-calculus textbook by Mr. David Cohen, I think it's Dr. David Cohen. The one that we use here at West LA College is the 6th edition pre-calculus, and it is section 13.2. Okay, now if you want to see that, then go ahead, see my lecture video on Math 260 on section 13.2. Okay, you go see yourself. Okay, so basically I want to say that for binomial series expansion, we have the first method using Pascal triangle. That's usually effective and efficient if the exponent is not too big. While if the exponent is larger, like 20, for example, then the coefficient is better used. We better use a combination method. Now, the problem with those two methods is that what if the exponent is negative? Okay, but before I go to the negative part, let's take a look on method 3. Suppose I want to find the expansion for 1 plus x to the power of 3. Now we know the expansion for x1 to the power of 3. That will be 1 to the power of 3 plus 3 times 1 squared times x plus 3 times 1 times x squared plus x cubed. Okay, where my a is 1 and my b is x. Okay, that gives us 1 plus 3x plus 3x squared plus x cubed. Now the thing is, I want to show you that this actually still what we get if we use Maclaurin. Suppose instead we apply Maclaurin method. Maclaurin method to get Maclaurin series. So fx equals to 1 plus x cubed. F0 is 1. When I take the derivative here, I will get 3 times 1 plus x squared, right? So f prime 1 is 3. I'm sorry, f prime 0 is 3. If I do another derivative, I get 3 times 2 times 1 plus x, where f double prime 0 is 6. And the third derivative of fx will be 3 times 2 times 1. And the third derivative of the function at 0 will still be 6. Clearly, the fourth derivative will be 0, right? Because it's already constant here. So the fourth derivative here will be 0. Then according to Maclaurin series, then fx, which is 1 plus x cubed, that is equal to f0 plus f prime 0 over 1 factorial x plus f double prime at 0 and 2 factorial x squared plus f triple primes at 0, 3 factorial x cubed. The fourth derivative at 0 over 4 factorial x to the fourth, and on. When I plug in numbers, I get this is 1 plus 3 over 1 factorial x plus 6 over 2 factorial x squared plus 6 over 3 factorial x cubed plus 0 over 4 factorial x to the fourth, and a bunch of zeros after. Which, if I simplify even further, I get 1 plus 3x plus 3x squared plus x cubed, and that's it. Okay, basically I want to say that if we do Maclaurin method to get the Maclaurin series, our Maclaurin series actually coincide with our binomial expansion if the exponent is a positive integer. Okay, now the thing is, what happens if the exponent is negative integer? If the exponent is negative integer, what happens? If the exponent is a negative integer, if the exponent is negative integer, clearly there is no Pascal triangle for that. Okay. Now, of course, we still have the notation for combination. Let's say, for example, if I have 1 plus x to the power of negative 3, we still can say that this will be, well, this is 1 to the negative 3, okay, and then plus negative 3 combination 1 to the negative 4 x plus negative 3 combination 2 1 to the negative 5 x squared. Notice that the exponents still add up to negative 3. You see that? The exponents still add up to negative 3. But then it means this 1 to the negative 5 here will never go down to 0. Right? My plan is according to our method 1, the exponent is supposed to go down to 0. 4, 3, let me use this. 4, 3, 2, 1, 0, and then we start, right? But if I start with the negative exponent, then it will never go down to 0. It will go to all the way. Okay, so this basically goes infinitely far. So negative 3 combination 3, 1 to the negative 6, x cubed, and so on and so forth. Okay, so the coefficient is not too hard. The coefficient is easy. The coefficient is easy. The thing is how to compute that. How to compute this. Then we actually use the idea that we have earlier. So negative 3 combination 1 means I start from negative 3. I have one factor on the top and one factor at the bottom. Okay. Now, for the negative 3 combination 2, it will be negative 3 times negative 2 over 2 times 1. Negative 3 combination 3. It means negative 3. I'm sorry. This should be negative 4 here. I subtract by 1. Okay, not negative 2. Subtract by 1. So negative 3 times negative 4 times negative 5. 3 factors on the top, starting from negative 3 over 3 times 2 times 1. Okay, now, such that now we have a new binomial expansion. Negative 1 plus x to the k will be 1 to the k, which is just 1, okay, which is just 1, plus k over 1 factorial x plus k combination 2x squared plus k combination 3x cubed all the way to infinity. Okay, now this is especially good for k is an integer and negative. In fact, it still works even if the k, for example, is 1/2 or 1/3. Okay. K is not an integer. It still works. It still works when k is not an integer. Okay. Now, clearly, if x is greater than 1, then it will be divergent. So you will see that radius of convergence here is equal to 1. Okay. In other words, the x has to be between -1 to 1, such that x to the n will converge to 0 for that to be convergent, right? Okay. At least by intuition. Now, how do we use this then? How do we use this? Suppose, for example, I want to find the binomial expansion for 1 plus x to the power of 1/3. Notice that this is the same to cube root of 1 plus x. Okay, now how do I do this? This is equal to, the first term will be 1. The second term will be the k over 1 minus x. The second term will be 1/3 times 1/3 minus 1, -2/3 over 2 times 1. Maybe I write it in notation first. How about that? In notation, it will be 1/3, choose 1. This is 1/3, choose 2. And then 1/3, choose 3 for x cubed. And keep on going. Okay, now 1/3 choose 1 is 1/3 over 1. 1/3 combination 2 is 1/3 times 1 minus that. 1 less than 1/3, negative 2/3 over 2 factorial. 1/3 combination 3 is 1/3 times negative 2/3 times negative 5/3 over 3 factorial. X cubed and on. So this is 1 plus 1/3 x minus 1/9 x squared plus, what is this, 27, 81, so over 80, and on the top I have 5, and on. Okay, now that's the binomial expansion for 1 plus x to the power of 1/3. Now our textbook used this illustration here. Our textbook example 4, let's call that example 4. In our textbook, example 9. So find the Maclaurin series, find Maclaurin series, which is the binomial expansion of fx equals to 1 over square root of 4 minus x. Now, I don't think you want to do derivatives, okay? I don't think you want to do derivative. You can, but I don't think that's what you want to do. In fact, I prefer to get 1 over square root of 4 out, and then this guy becomes 1 minus x over 4, which is basically 1/2 times 1 minus x over 4 to the power of negative 1/2. Okay, then that 1/2 stays, this 1/2 stays, and this guy is the one I change into binomial expansion, which is the summation of negative 1/2 combination n, the n start from 0 to infinity of x over 4 to the power of n. Negative, I'm sorry. So I substitute, this is 1 plus negative x over 4, right? Now that negative x over 4 is the one I put here. Okay, now then what will the binomial expansion? Let's say we want to do the first 4 terms. Okay, the first 4 or 5 terms then. So fx equals to 1/2 times, the first term is 1. Yeah, when n equals to 0, right? That's 1. And then the second term will be plus negative 1/2 combination 1, negative x to the 4th to the 1, plus negative 1/2 combination 2, negative x to the 4th squared, plus negative 1/2 combination 3, negative x over 4 cubed. How many terms here? 4 terms. One more. negative 1/2 combination 4, negative x over 4 to the power of 4, and keep on going. Now let's compute. This is 1/2. This is negative 1/2 times negative x over 4. This is negative 1/2 times negative 3/2 over 2 times 1. And then I get x squared over 16 plus negative 1/2 times negative 3/2 times negative 5/2 over 3 factorial negative x cubed over 64 plus blah 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 times x to the 4 over this is 64 times what? 260? 256. I just show you how to compute it. It's tedious, but therefore pay attention. Okay, be detail oriented. This is 1, and then there will be this will plus 1/8 x plus 3 over what is this? 8 times 16, 2 to the 128 square, and then this will be still plus what is that? 2 to the 4th, 2 to the 4th times 64. It's 1000 something. And this is plus 1024. And on the numerator, I have 5 x cubed. And the last one, sorry, I was borrowing this position here. The last one, it will be plus, hold on, that will be negative 1/2 times negative 3/2 times negative 5/2 times negative 7/2 over 4, 3, 2, 1 times x to the 4th over 256. That will still be positive. The 3 cancels. That one is easy. But I have 1, 2, 3, 4, 5, 6, 7. 2 to the 7 times 256. Ooh, what is 2 to the 7? That's 256 squared. Ooh, that's a very big number. And on the top, I get 35. Let me use my calculator.
I think it's 128 times 256.
Yeah, 128. So that will be over 32,768 x to the 4. And then to make it even smaller, this is equals to, I multiply the 1/2 in. So 1/2 plus 1 over 16x plus 3 over 256x squared plus 5 over 2048x cubed plus 35 over 6, 5, 5, 3, 6 x to the 4, and on. So you see that as long as the magnitude of x is less than 1, this actually converges quite fast. Notice that this converges a lot faster than this one. Take a look at the ratio. You multiply by something a lot smaller, right? Okay, so that's one example of this binomial expansion with either negative exponent or fractional exponent. Okay, I know it's tedious. And that's why they put it at the last. If you try to do that by derivative, it will be a lot worse, because the derivative of this number here, this function here, you have a lot of square root, right? Yeah, you have a lot of square root. Well, anyway.
So, Professor,
Uh-huh.
does that mean that like what you just said? That means that there's always a way that we can like simplify it or change it, because like how you did it at the beginning, how you made it, how you factored out the radical 4. So you're saying
Yes.
that for these problems, there's always going to be another method besides doing the derivative, correct?
That's right. So that's why I teach you this expansion instead of doing derivative. Instead of doing derivative, we actually manipulate and take advantage of the binomial expansion that we learned for positive integer. Yeah. Okay, so so actually, by the way, that answer a question. Suppose, for example, I make up my own question. Suppose, for example, I want to compute square root of 3. Okay, I want to compute square root of 3. Hold on. What is the radius of convergence here? I think I said it wrong. The radius of convergence is actually 4. So it's 4 because I replace this guy, right? My position here, my position for this, right? My position for that is the one, so absolute of negative x over 4 should be less than 1, right? So absolute of x should be less than 4. Does it make sense? So my radius of convergence is actually not 1. I said it wrong earlier. It's actually 4. The radius of convergence equals to 4. Okay? Now, anyway, suppose I want to compute square root of 3 and with accurate to 5 decimal places. I want to make it accurate to 5 decimal places. Then I may approach it this way. I will see let fx equals to square root of 4 minus x. And what I need to do is actually to find f1 later on. Okay, I want to find f1. But then this is actually 2 square root of 1 minus x over 4. Is it right? And then I do the expansion. This is 2 times 1 minus x over 4 to the power of 1/2. So this is 2 times the series from 0 to infinity of 1/2 combination n negative x over 4 to the power of n. Okay, now the question then, because I want 5 decimal places, right? I want 5 decimal places. Then the first question is how many terms? How many terms is needed? How many terms is needed? Well, If you want to see that in an easy way, I just need this guy here. I just need this guy here. Actually, it's a lot less than what I'm about to do. But I can see, oh, this guy here has to be less than 0.00001. Is that right? And by the way, my x later on will be replaced by 1. Is that right? My x later on will be replaced by 1. So I just need 1/4 to the n should be less than 10 to the power of -5. Okay? In other words, then how to do this actually? This is 4 to the power of -n less than 10 to the -5. If I do the reciprocal, then 10 to the 5th should be less than 4 to the n. Apply log base 10, so 5 should be less than log base 10 of 4 to the n. Let me move the 4 here. So n has to be greater than 5 over log 4. Now 5 over log 4 will be 8 something. This is 8.3 something. So use n equals to 9. So I go 9 terms. Notice that very likely I don't need to go up to 9 terms because this guy here actually goes to 0 very fast too. Okay, it goes to 0 very, very fast too. Okay. Now then, so 9 terms guaranteed the error to be less than 10 to the -5. Okay. Now then, let me expand that a bit further. So this is equal to, let me go back. So square root of 4 minus x, this is equal to 2 times, the first term is 1. The second term is 1/2 combination 1x. Oh, I'm sorry. Not x. That's -x over 4. -x over 4 to the 1 plus 1/2 combination 2 -x over 4 squared plus 1/2 combination 3 -x over 4 cubed all the way to the 9th term, which I said earlier is actually, you will see it's actually not necessary to go that far. Okay, it's actually not, because this guy actually converges quite fast too. Okay, it goes quite fast also. Then this is equal to this is 1, actually this would be negative 1/2 times x over 4, and then this will be plus 1/2 times -1/2 over 2 times 1 over x squared over 16 plus 1/2 times -1/2 times -3/2 over 3 to 1 times -x cubed over 64, so on and so forth. So this is 2 times 1 minus x over 8. I think this is minus again, huh? X squared over, what's that? 2 to the 7, 128. And then this minus again. Oh, we keep on minusing. The 3 cancel, so that's x cubed over 2 to the 4th times 64, 1024, and then so on and so forth. Okay, so square root of 3 is equals to square root of 4 minus 1. It's basically replacing the x by 1. Okay, so far I did up to the third term only. Okay, let's see. Let's see if I use my calculator. So that will be 1 minus 1 over 8 minus, what's next? 1 over what?
128.
128, and then minus
1 over 1024.
So let's say I go up to this, the third term only, up to n equals to 3. So I get 0.86621. It's equal to 0.86621. Of course, we have extra. Multiplied by 2, that will be, see, that will be 1.73242. That's 1.73242. So notice that I go up to n equals to 3 only. Right? This is n equals to 3 only. Okay? Now, but let's see the actual value of square root of 3. So the square root of 3 equals to that. So at least I'm correct up to the third decimal place already. Right? And yes, if I go on more terms, then I will get what I need. Okay. I wonder if I can use Excel for this though. I'm not sure if I can, but let's try. Let me see, where's my Excel? Oh. How to get my document? Give me a second. This is what happens if you use your sister's computer. Spreadsheet. Let me see first if I have that function, the combination function. So combination math. Is there any combination function? Combination. Number chosen. Okay. So if I use the number to be 0.5, and let's say this is 3, we get the same thing. Oh no, it's not doable. What's wrong? See, and this cannot be used anymore, huh? So 1/2 earlier, right? No, it's still not doable. Okay, so Excel cannot handle it. Let's use calculator. Can calculator handle it? So let's say 0.5 combination 3. Now you see it's not doable, right? So basically I want to say that your calculator can only do as much as maybe calculus 1, right? Okay, no, the calculator cannot do this anymore. You see, even if you use Excel. Why? Because the way our calculator working on this, like the way our calculator working on this, like 1/2 and then let's say 3 here, for example, it actually does the following: 1/2 factorial over 3 factorial, and then 1/2 minus 3 factorial. But the thing is, the way they design this 1/2 factorial, the way they design it is always as the following. Let's say if I have 4 factorial, then they will do recursively down to 1. 4 times 3 times 2 times 1. But then if you start from 1/2, there's no way you end at 1. There's no way. You'll be 1/2, negative 1/2, negative 3/2, and our calculator will keep on going, keep on going until it reach 1. But it will never get 1. You see? Okay? That's why it fails to do it. Our calculator does this algorithm, which is different from the way we did it earlier. Okay? So unfortunately, then you need to know what to do. I somehow think if I go one more terms here, then I get what I need. I think so. Yeah, I think so. If I go one more term, because it's already very small in the 4th term. Well, anyway, I don't want to go too much. Notice that it takes me 1 hour just to explain this binomial expansion. Okay, but make sure you put this in your toolbox. Make sure you put this in your toolbox. Where's that? This thing here. Make sure you put this in your toolbox. Make sure you put this in your toolbox. Okay, make sure you put that in your toolbox where the k can be anything. The k can be anything. It doesn't have to be positive integer. It doesn't have to be negative integer. This can be anything. Okay, now another topic that I would like to do here, this is actually a smaller topic compared to binomial, is about multiplying Maclaurin series. Multiplying and dividing. Multiplying and dividing of dividing power series. One very well-known case, or maybe I do this case first. For example, I want to find the power series or let's say e to the x times e to the x times, let's say, natural log of 1 plus x. Now both of them are in our toolbox. Both of them are in our toolbox. E to the x is 1 plus x plus x squared over 2 factorial plus x cubed over 3 factorial and on. While natural log of 1 plus x will be natural log of 1 plus x will be, oh, I forget. When I look at my toolbox, I get x minus x squared over 2 plus x cubed over 3 and on. Then what happens if I multiply them? When I multiply them, I basically multiply the power series. 1 plus x squared over 2 plus x cubed over 6. Let me go one more term. X to the 4 over 4 factorial, that's 24. And on times x minus x squared over 2 plus x cubed over 3 plus minus x to the 4 over 4 and on. Our issue is how to multiply this power series. Both of them infinite series, okay? Now, what we will do, we will just get the first couple terms. Remember that these series are all convergent. So eventually, we just need to get the first few terms, right? Okay. Now, suppose, for example, I just want to have 5 terms. Get up to x to the 4th. Let's say I get up to x to the 4th. Sometimes the question also say get the first 4 non-zero terms, let's say. Okay, I don't know, depends on the question. So the first thing I will do is think about the lowest exponent possible. The lowest exponent possible is x, is it right? That's the smallest possible, so that's x. Now then after that, I would like to know how to get x squared. How to get x squared, by the way. To get x squared, I need to multiply this one with this. Okay, but also this guy with this. Okay, so the first one gives me negative 1/2 x squared. The second pair gives me x squared. The sum is 1/2 x squared. Next, how about x cubed? To get x cubed, it will be this guy times this guy. Okay, and then this guy times this guy. And this guy times this guy. That's to get x cubed. So I get 1/3 x cubed for this pair. This is negative 1/2 x cubed for that pair. Okay, and then this guy here is, hold on. This guy with this guy with this. This is 1/2 x cubed also, is it right? So I get 1/3 x cubed. Now, can you try the 1 to the power of 4? Plus what to the power of 4? I give you a hint. to the power of 4, you need this pair, and then this pair, and then this pair, and then this pair. There are 4 pairs. Okay, now later on, after you get that, oops, plus, I will just do dot, dot, dot. Let me give you maybe 1 minute for that. So this pair here, I get negative 1/4 x to the 4th. This pair here, I get positive 1/3. This pair here, I get negative 1/4. This pair here, I get positive 1/6. So negative 1/4 minus 1/4 plus 1/3 plus 1/6. Ooh, this is negative 1/2. That's 0. Let me check. That's not really right. At least I don't believe it. Let me check my computation again. Negative 1/4 for that. Positive 1/3. Negative 1/4. Positive 1/6. Oh, that's 0. That's right. That's 0. That's 0 here. Okay. And then you go to the power of 5. Okay, you go to the power of 5 if you want me to. Well, anyway, so right now we get this expansion. Okay, that's for multiplication, which if you say this is hard, this is actually on the easy side. The hard side is, for example, a well-known example, the hard one is tangent. Tangent x is the quotient of sine x over cosine x. Which is, I will just do couple terms, okay? But even that couple terms is already quite messy. It will be 1 minus x, I'm sorry, sine is an odd function, no, it should not start from 1, it should start from x. So this is x minus x cubed over 3 factorial plus x to the 5th over 5 factorial and on. I just do 3 terms on the top, and I will do 3 terms at the bottom, minus x squared over 2 factorial plus x to the 4th over 4 factorial and on. Let me make it nicer. This is x minus x cubed over 6 plus x to the 5th over 120 and on over 1 minus x squared over 2 plus x to the 4th over 1/4 and on. Now I will divide this. X cubed over 6 plus x to the 5th over 120 and on divided by 1 minus x squared over 2 plus x to the 4th over 24 and on. Now, we will start. 1 times what give you x?
X.
Hmm?
Just x, right?
Just x, that's right. So I will multiply the whole series here by x. Okay, I will multiply the whole series there by x. By x. So 1 times that x is x. Right? And then negative x squared over 2 times x is negative x cubed over 2 plus x to the 5th over 24 and on. Now subtract. Negative 1/6 minus negative 1/2. What's that?
2x cubed over 6, right?
That's 2 over 6. That's
2/3.
1/3, right?
Or 1/3.
Positive 1/3. So this is 1/3 x cubed. Now how about this part here? 1 over 120 minus 1 over 24.
I got 4x to the 5th over 120.
Okay, so negative 4 over 120. I will reduce that to be negative 1 over 30. Okay, so this is negative 1 over 30 x to the 5th. Now, of course, that's still dot, 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 right? I plan to do only 3 terms. Okay, so 1 times what gave me 1/3 x cubed?
1/3 x cubed.
Plus 1/3 x cubed. Okay, so that will be 1/3 x cubed here. And then minus 1 over 6 x to the 5th, right? And on. So that's good. Do you want to go one more term?
Yeah, sure.
No, I don't want to. It's too long. It's too long. You just need to see the principle, right? Okay, so assume in your test later on, I may ask you, okay, write the power series for tangent x up to with 4 non-zero terms. Yeah. The first 4 non-zero terms. Then here I will get 3, right? Now later on, the 4th one, you actually need to get the 4th term here, x to the 7th thingy, and here you need to get x to the 6th thingy. Okay, so negative 1 over 30 minus negative 1/6. That's negative 1 over 30 plus 5 over 30. That's 4 over 30, which is 2 over 15, but positive. So this is positive 2 over 15 x to the 5th. So here I just need then plus 2 over 15 x to the 5th. And on. Okay, let me see. Our textbook seems not to ask. Oh, it does. It does. Actually, our textbook have that on page 788. Our textbook has that on page 788. And it does 3 terms only also. Okay, it just happened to be the same. I should have cheated from here. Anyway, those are the basic things that we need to know from this section. Not that basic, but it's enough to allow us to do a lot of things here. Okay. I want to get a break, but I don't really want to either. Let me just go on. So up to here, we are done with the material. With the topics. What I will do next is we'll do more examples. Okay, let's say, for example, I do number 26. So I do problems from the book right now. Maybe I do in the next page, so that later on I don't have a big things to save. For example, I do number 26. Number 26, that is on page 789.
Professor, I'm sorry, when you say we're done with the material, you mean all the material for the class?
Yeah,
Okay, good.
yeah, so what I do in the next page here, I basically do more examples from this 11.10.
Okay, great, thanks.
Number 26, do the expansion for cube root of 8 plus x. Okay, let me modify this. I factor the cube root of 8 out. So inside I get 1 plus x over 8. I'm sorry, actually cube root here. So this is 2 times 1 plus x over 8 to the power of 1/3. Okay, now this is equal to 2 times the sigma from n equals 0 to infinity of the combination, and this will be x over 8 here to the n. But how about this guy? It says use table 1. Well, basically look at your toolbox. This will be the exponent 1/3, and this is n. Okay. Where the radius of convergence, I replace this guy, I replace the x supposed to be here by x over 8. So magnitude of x over 8 should be less than 1, absolute of x, therefore less than 8. That's our radius of convergence is 8. Suppose I will need to expand this for the first couple of terms. Let's say I do that for the first 3 terms. Okay, so up to n equals to 3. So this will be, when n equals to 0, that's 1. That's easy. Okay, plus 1/3 combination 1 x over 8 plus 1/3 combination 2 x over 8 squared. Plus 1/3 combination 3 x over 8 cubed and on. This is 2 times 1 plus 1/3 times x over 8. This is 1/3 times -2/3 over 2 times 1 times x squared over 64. Wow, it converges really fast. And this is 1/3 times -2. I'm sorry, yeah, -2/3 minus 1, that will be -5/3 over 2 times 2, 1 times x cubed over a cube. This is 2 times 1 plus x over 24 plus, no, that's minus 9 times 64 is what? The 2 cancels, right? The 2 cancels. So 9 times 64 is 500. This is x squared over 576. This is then plus 5 on the top. 3 to the 4th times 8 cubed. That's 41,472. Okay, so that's the expansion. If I multiply the 2 in, that would be 2 plus x over 12 minus x squared over, what is this, 188. Okay, and then plus 5x cubed over 20,736. And on. Just for fun, suppose I want what is the cube root of 9? That's the same to cube root of 8 plus 1. So I replace the x by 1. If I use my calculator, plus 1 over 12 minus 1 over 288 plus 5 over 20,736. I get this is approximation because I stop at the third term. I get 2.08010. Okay, but the actual value of this is 9 to the power of 1/3. This is 2.08008. 3823. So notice that it is actually accurate to 4 decimal places. Accurate to 4 decimal places. Because if I round it to 4 decimal places here, I'm good. Right? So this is accurate to okay. That's for number 26. That's for number 26. Let me go on. Do you have any question you want me to do on this page? Let's say, how about number 34? Number 34, the question is, again, use the Maclaurin series in table 1 to obtain Maclaurin series for fx equals to x squared times natural log of 1 plus x cubed. Now, the x squared is easy, just leave it there. Now, how about the expansion of ln natural log of 1 plus x? That's the series from n equals 0 to infinity, -1 to the power of n minus 1, and then x cubed to the n over n. So this is x squared, the alternating series. Okay, we should start from 1, not from 0. From 1, not from 0. Of x to the 3n over n. Now, then I will multiply the x squared in. X to the 3n plus 2 over n. Okay, in case you need the radius of convergence, notice that the radius of convergence for this, your ln, the radius of convergence is absolute of x cubed here. Absolute of x cubed here should be less than 1, which implies that absolute of x, if you apply cube root, is less than 1. The radius of convergence is equal to 1. Okay, so the x that you use should not be outside of this interval. Okay, the x that you use should not be outside of that interval. That's for number 34. How about number 44? Calculate 1 over 10th root of e to 5 decimal places. Okay, 1 over 10th root of e is equal to e to the power of -1/10. Right? Okay, now e to the x is given by the series, the power series x to the n over n factorial. Correct? So if I replace that x by -1/10, so e to the -1/10 is the same to the infinite series from 0 to infinity of -1/10 to the n over n factorial. Which is, by the way, what I really need here is alternating series. This is -1 to the n over 10 to the n and factorial. Now you want your error will be less than 10 to the negative 5 decimal places, right? Okay, but we also know that the error will be less than the positive term dn. In this case is 1 over 10 to the n and factorial. Right? Okay, now then set this to be less than 10 to the negative 5 and solve for n. And then solve for n. So 10 to the 5th is less than 10 to the, hold on, do reciprocal, yeah. This is 10 to the n times n factorial. And I believe n equals to 4 is good enough. Yeah, this is 10 to the 4, and 4 factorial is 24. Right? So I just need 4 terms. Okay, I just need 4 terms. Up to n equals to 4. So when n equals to 0, that's 1. When n equals to 1 is minus 1 over 10. When n equals to 2, that's 1 over 200. When n equals to 3, with that shipping height. When n equals to 3, that would be negative 1 over 6,000. And when n equals to 4 plus 24,000. That's all you need. Okay, so I will use my calculator. 1 minus 110 plus 1 over 200 minus 1 over 6,000 plus 1 over 240,000. I get 0.9048,375, which if I round to 4 decimal places, 5 decimal places, 0.9048,4, right? Okay, now the actual value is, let's see, so e to the power of negative 110. The actual value is 0.9048,37418. Wow. If I round to 4 decimal places, this is what I get. Hold on. As I remember, I don't need to go to 4. Yes. N equals to 4 will give me what I need, but it means I just need to go up to the third term for alternating series. Let's see. 1 minus 1 over 10 plus 1 over 200 minus 1 over 6,000. Yeah, if I go only 3 terms, yeah, supposed to be only 3 terms, so I don't need 4 terms. For alternating series, that's the error there, which means I just need to go to n equals to 3, and that gives me 0.9048,333. So you see the error on the 5th decimal place. The error is on the 5th decimal place. To be more precise, it's actually here. it start to be different at the 6th decimal place. Okay, so I just need 3 terms. So do you think it's really nice that to be accurate to 5 decimal places, you just need to go 3 terms? I'm sorry, actually 4 terms, but up to from n equals 0 to n equals to 3. Next, how about number 48? One of the main use of power series is to help us doing limit and integration. Let's say, for example, number 48, we want to integrate e to the x minus 1 over x. This is so not doable analytically, though. Okay, however, I can do the following. Take a look. That e to the x is 1 plus x squared over 2 factorial and on. Basically, this is the summation from n equals to 0 to infinity of x to the n over n factorial. Now, imagine if I subtract by 1. So I actually start from this n equals to 1. Is that right? So it will be just the same series, but I start from 1. Is it okay? Now then, how about if I divide by n? Divide by x. So x here becomes 1, x squared there becomes x. Or basically, this is the series from 1 to infinity of x to the n minus 1 over n factorial. Okay, so, and we can say integral e to the x minus 1 over x dx is the integral of this infinite series. Which is the series of the integral. Now, when you integrate that, you will have the series from 1 to infinity x to the n over n times n factorial. Don't forget, that's constant. Okay. Number 58. So the question is, find the limit for x going to 0 of tangent x minus x over x cubed. Now it says here that if we use L'Hopital rule, we need to do L'Hopital rule 3 times. Okay, but if you happen to know the extension of tangent x, let's see first. What is tangent x again? Tangent x is x plus, I don't remember. Let me go back. x plus 1/3 and then 2/15. That's 1/3 x cubed, 2/15 x to the 5th, and on. So tangent x minus x will be 1/3 x cubed plus 2/15 x to the 5th and on. Now suppose I divide by x cubed, and so x here and x cubed here, then I will get 1/3 plus 2/15 x squared and on. Now then apply limit. Limit x approaching 0 of this expression tangent x minus x over x cubed equals to limit x approaching 0 of 1/3 plus 2/15 x squared and on. X squared and then x to the 4th and on, right? But that's basically applying x equals to 0. So the limit is 1/3. I did number 62, but how about number 60? Oh, yeah. Number 60, find the power series representation for y equals to secant x. That is 1 over cosine x. Cosine x representation is 1 minus x squared over 2 plus x to the 4 over 4 factorial minus x to the 6 over 6 factorial times 30, so 720 and on. So secant x basically this quotient. This is 1 divided by 1 minus x squared over 2 plus x to the 4 over 24 minus x to the 6 over 720 and on. One times 1 give me 1. And then when I subtract, I get x squared over 2 minus x to the 4 over 24 plus x to the 6 over 720 and on. And then I get plus x squared over 2. X squared over 2 here, and then minus x to the 4 over 4 plus x to the 6 over 48, and then subtract again. So that will be positive 5 over 24 x to the 4th here. And then 1 over 720 minus 1 over 48. Dude, I don't even know what's the LCD. Let me use my calculator. Lazy guy. So what's that? 1 over 720 minus 1 over 48, is it? Now that gives me decimal. I want the fraction. Okay, then to change that to fraction, I do this. Negative 7 over 360. Oh, you see? Lazy guy. That's negative 7 over 360. So the next term will be plus 5 over 24 x to the 4 minus 5 over negative 7 over 360 plus 5 over 4. Plus 5 over 48. Change it to fraction. 61 over 720. This is 61 over 720 x to the 6. So the last one will be plus 61 over 720 x to the 6 and on. Okay, that's the power series for secant x. In this case, I get the first 4 non-zero terms. Oh, the question only asks us to do the first 3 non-zero terms. Okay.
Yeah, you got ambitious there, but that's cool.
I usually it's 4, by the way. Usually 4 non-zeros. Okay, well, anyway, I will go on further. The last part here is actually most interesting one, in my opinion. Number 64. Number 64, the series from n equals 0 to infinity of negative 1 to the n pi to the 2n over 6 to the 2n times 2n factorial. Now, why I make this, I say that this is interesting because you need to memorize the toolbox. You need to memorize this and see which of these actually similar to that. Okay, we have negative 1 to the n. We have negative 1 to the n, and we have 2n factorial. Look at this table here. Which of them has that pattern?
The cosine?
The cosine x, that's right. So let me rewrite this into something very similar to cosine x. So I will get negative 1 to the n. Okay, and then I write pi over 6 to the 2n over 2n factorial, right? But this is equals to cosine x, where the x is pi over 6. So this is radical 3 over 2. Okay, you should be able to kind of like connect the dots in between. Number 66. The series from 0 to infinity of 3 to the n over 5 to the n and factorial. Let me give you a hint. I will rewrite this as 3/5 to the n over n factorial. Which one? Which of this function in which you replace the x by 3/5 give you what you need? That's why I say you have to memorize. If you don't memorize, you can look at this table and it takes you too long.
Is it e to the x?
That's e to the x. So this is equal to e to the 3/5. Okay, what we did in the past is we have e to the 3/5 and then we write the power series expansion. Now we actually have the series and then compute what is the exact value. Okay, number 68, or is number 68 interesting? I don't think so. Is it? Number 68, we have this 1 minus ln2 plus ln2 squared over 2 factorial minus ln2 cubed over 3 factorial. What is the power series? This is 0. This is 0. This is infinity. That's -1 to the n of ln2 to the n over n factorial. Oops. You know what? Let me put this in. This is negative ln2, right? To the n over n factorial. Oh, okay. This is e to the negative ln2. That's 2 to the power of -1. So this is 1/2. That's number 68. Do I want to do more? How about number 70? They look so ugly. Last one, number 70. I don't want to do anymore. So 1 over 1 times 2 minus 1 over 3 times 2 squared. 0. No, 3 cubed. 2 cubed. Plus 1 over 5 times 2 to the 5th. Minus 1 over 7 times 2 to the 7th. And on. Let's try to rewrite that using summation notation. Start from, I think that will start from 1, 0, infinity. Let me take care the 1 over 1, 1 over 3, 1 over 5, 1 over 7. It's alternating, so that's -1 to the n it starts from positive, right? And here my n is 0, starting from 0. Okay, and then it will be 1 over 2n plus 1. And then 1/2 to the power of 2n plus 1. Oh, what is this? Oh, it seems to be tangent, huh? Yeah, it seems to be tangent. So this is equal to tangent inverse of 1/2. Okay. Tangent inverse of 1/2 is my calculator happened to be in degree mode. I need to change that code. Let me see the mode. Yeah, it has to be in radian mode. So tangent inverse of 1/2 is 0.46365. 0.46365. If I go to 5 decimal places. Okay, that's basically it. What I want to go over this semester, actually. Your suggested homework will be from this 11.10b. Number 25, number 25 to 37. And then 43 to number 69. Again, just do the odd ones. Okay, now that's basically it for this semester. Hold on, is there anything else I want to do? Oh, you know what? Let's see.
Professor,
Mm-hmm.
which questions or what sections will be on the exam
What section
prior
will
to
be
the final?
The test 4, you mean, right?
Yes, yes.
Yeah, test 4. What is the last one we had? I think we have up to 11.1, right?
Think so?
One. I think so.
Somewhere in my notes.
Yeah, I think the cutoff for my test 3 always 11.1. So your test 4 will be from 11.2. Test 4 will be from 11.2 up to 11.10.
Thank you.
Mm-hmm.
All right.
Okay, let me make you busier. How will you study? Of course, this is not my source of problems, but you can try to take a look on this. On my website, where's my website? Arjuna.com. Click on my face. And go to Test Playground, USC Past Finals. And then, let's say, fall 2008. Fall 2008. 2008. If you want to know what your final looks like, it will be similar. Of course, they don't have parametric and polar, as I remember.
Parametric what? I'm sorry, kind of
Parametric and polar. Yeah, they actually cover the same material to ours, but they have something else with work, I think. But they don't have center of mass. They don't have polar and parametric equation thingy for their final. Not this one, not exam, not problem 4 here. Not this one. Not this one. Not this one. Sequence, that's something we have done last time. How about this? Oh, this one is easy. This is what? Okay, do you see this question, problem number 9 here?
Yes.
Okay, if you look at this question, what do you think your approach be?
A P series, like comparison test.
That's if you just need to find if it is convergent, divergent. But the problem here, they have determine the sum.
Oh, what's it called? Telescoping.
Telescoping, partial fraction decomposition.
Mm-hmm.
Okay, how about this one? Still telescoping, actually. How do you do that, Thomas, by just looking at that? Oh, of course, experience. Experience. Well, by the way, when I say experience, I did say that in actually a negative tone, not in a positive tone. Not, this is off record, okay? This is off record. Somebody once said that if you meet a guy who kind of like a perfect guy to date, very likely it's because of experience. You know what I mean, right? It means that person maybe break up for many, many times already. Okay, let's see how do we approach this problem here. Let's write the first couple terms. This is when n equals to 1, there will be ln 1 over 4 plus ln 2 over 7.
Oh, we still got the exam screen.
Oh, yeah, that's right. Thank you. Here. Plus ln 3 over 10, right? And on. So this is actually equals to ln of 1 over 4 times 2 over 7 times 3 over 10. I wonder if there's any way for me to cancel something. I have no idea. Oh, what am I doing? Duh, this is actually divergent. This is divergent. I'm thinking too hard. Do you know why this is divergent? I'm thinking way too hard. So we have that, so the a sub n equals to natural log of n over 3n plus 1, right? Okay, which is equals to natural log of, if I divide by n on the top, n at the bottom. Notice that this converges to ln 1/3, which is not 0. By divergence theorem, actual divergence test, therefore this series is divergent. Okay. Yay, I do USC problem. Okay, that's for part B. Let's go on further. Why go that far? Hey, stop. That was number what? Number 9? Early. This guy, right? Let me go further down. Find the radius of convergence and interval of convergence for this power series. Okay, let me quote that first. Boom. Boom. I really so want to just say, you know what, that's it for today, that's it for this semester, see you on Monday for the test, right? I can. Yeah, but then let's do some USC problems. Now, the reason I show you USC problems, I'm not trying to say that, you know what, USC problem is so hard. It's actually the other way around, okay? A lot of you think about UCLA, USC students, that they must be so smart, but I am trying to show you what I teach you is something that you're supposed to get even at those universities, okay? How do I know that I teach up to their levels? Do their problems. That's how we know. Okay, so if you have any instructor saying that, you know what, you can just do this, and those problems not related to what they do at university level, then they teach you something irrelevant, right? Okay, even though I have to admit there are times university teach you something irrelevant for your real life later on, but that's another story. Okay, at least when you transfer, what you learn at West LA College is really transferable to at least USC, right? Okay, now don't talk to me about Cal State Dominguez Hills. I'm sorry. Okay, let's see here. We want to find the radius of convergence. How do we do this again?
Do the ratio test.
That's right. Ratio test, I do
Absolute value
of
of
the
the
next
function with n
term
plus 1.
over.
Oh, we've got the exam screen again. Yes, exam
Oh,
screen
I'm
again.
sorry.
Sorry.
Thank you. And then this will be, okay, then that will be n plus 1 over n plus 1 squared plus 1 times x plus 3 to the power of n plus 1 times the reciprocal of that. That would be n squared plus 1 over n times x plus 3 to the n in absolute value. Let me factor absolute x plus 3 out first. That one is easy, right? Okay, and then as for the n's, all of them positive numbers, because we will bring n to the infinity. So this is n plus 1, n squared plus 1 over n plus 1 squared plus 1 times n. This is absolute of x plus 3. On the top, let me FOIL that, even though I don't really want to do it there. So that would be n cubed plus n squared plus n plus 1 on the top. At the bottom, I will be n squared times n cubed. 2n times n will be 2n squared. And then 2 times n, that's 2n. That's equals to absolute of x plus 3 divided by n cubed. This will go to what?
We'll approach absolute x.
Absolute of x
Plus
plus 3.
Plus 3.
Okay.
Plus 3.
And we want this to be less than 1. right? So the radius of convergence is 1, and interval of convergence will be between -1 to 1 for x plus 3. So x will be between -4 to -2. Okay. Now, the thing is, do they ask for yeah. So the radius of convergence is already answered. Okay, but we need to check the endpoints, right? We need to check what happened when x equals to -4 and what happened when x equals to -2. Is it okay?
Mhm.
So the series is what again? -4. So I get series n equals to 0 to infinity of, oh, actually from 1. From 1 to infinity, and then n over n squared plus 1, but this becomes -1 to the n, right?
Mhm.
So this is alternating series. Where Bn is n over n squared plus 1. I need to show that this is decreasing. Need to claim that n over n squared plus 1 is decreasing. And later on, I need to show that the limit is 0. Okay, I think it's pretty clear, huh, that it is convergent to 0. So I divide by n squared, right? It converges to 0 as n goes to infinity. That one is easy. Okay, and then how to show that it is decreasing? Then I need to show that when I replace n by n plus 1, I need to show that this is less than n over n squared plus 1. But that's if and only if n plus 1 times n squared plus 1 is less than n times n plus 1 squared plus 1. That's if and only if this is n cubed plus n squared plus n plus 1. This is n cubed plus 2n squared plus 2n. Subtract, subtract, subtract. Then I get 1 is less than n squared plus n. Now this is true for n greater than or equals to 1. Okay, so this series from 1 to infinity of -1 to the n over n squared plus 1 is convergent by alternating series test. Now the thing is, how about when x equals to -2? Check when x equals to -2, the series becomes that will be n over n squared plus 1 to the n. Right? That's basically this series. Okay. Is this convergent or divergent? Nobody says anything. Okay.
Convergent.
Huh?
It will be convergent.
Notice that this is actually similar to 1 over n. Right?
Oh, I see.
Okay, so I will do limit comparison tests. Okay, I will do limit comparison tests. So compare to this series 1 over n. Now notice that that harmonic series is divergent. Okay, so we get 1 over n big over n squared plus 1. That's equal to n squared plus 1 over n squared, which is 1 plus 1 over n squared over 1 that converges to 1. Right? Okay, which is a positive constant. So by okay, so we know this is which is divergent. Why is it divergent?
They
For-
share.
No, for this one,
Test.
Why is this divergent?
Oh, why is that divergent?
Limit comparison test.
Limit comparison test is to show that this
Those two
is
share
divergent.
behavior.
Okay, but my question is, why is this divergent
Oh, harmonic series.
by harmonic series? Or you can also say P series P equals to 1. Divergent by harmonic series. And by limit comparison test, the series from 1 to infinity of n over n squared plus 1 is divergent. So finally, so the interval of convergence will be from -4 to -2, -4 to -2 union -4, but not including -2, right? That will give me -4. That's the interval of convergence. Okay, that's for this number. I don't remember what number is that. Let's go back. That's number 10. Let's go on further. Find the first 6 terms of Taylor approximation of cosine x at pi over 4. Taylor approximation. So find Taylor approximation for cosine x at a equals to pi over 4. Don't forget that fx equals to fa plus f prime a over 1 factorial x minus a plus f double prime a over 2 factorial x minus a squared, so on and so forth. Okay, let me see what's the question again. The first 6 terms. Oh shoot, somebody made me work hard. So I need to do 6 derivative. Okay, so fx equals to cosine x. So what is f pi over 4? Radical 2 over 2. Is that right? Cosine pi over 4, right? So f prime x is negative sine x. So f prime pi over 4 is negative radical 2 over 2. F prime double prime x is negative cosine x. F double prime of pi over 4 is negative radical 2 over 2. I need 6 terms, so up to the 5th derivative. Do you see some pattern here, by the way? So this is equal to, so cosine x centered at pi over 4 is radical 2 over 2 minus radical 2 over 2 over 1 factorial x minus pi of 4 plus, actually still minus, minus radical 2 over 2 over 2 factorial x minus pi over 4 squared, the third derivative plus radical 2 over 2 over 3 factorial x minus pi over 4 cubed. And then the next derivative of that is cosine, which will give me positive. So plus radical 2 over 2 over 4 factorial x minus pi over 4 to the 5th. And the 5th derivative, that will be negative. I'm sorry, this is to the 4. This is to the 4. Okay, now make it nicer. This is square root of 2 over 2. Let me factor that out. So 1 minus, this is 1, x minus 1 half plus 1 over 6 plus 1 over 24 minus 100, 1 over 120 x minus pi over 4 to the 5th. Okay, now this is the first 6 terms, the first 6 non-zero terms. Okay, I factored radical 2 over 2 to make the coefficient looks nicer. Okay, let's go back to the question. That's problem number 10. Oops, not this one. This one. This one. Oh, that's number 11. Maybe one more question. We did this before. That's all. Okay. Well, of course, the reason I share this with you is because that's actually one source for you to study from. Okay, this test here. Okay, suppose I make 4, 7. They have that. Yeah, they have that. So you can study from here too, right? They have series. Number 6, number 7. Number 7 here is similar to the one that we did earlier, the last type of questions. Okay, number 8, radius of convergence, interval convergence. So that's actually a common question. Okay. And then number 9. Well, anyway, that's where I want to stop here then. So your tests on Monday will be from what to what? From 11.2 to 11.10. I will post the test at. I'll post the test at what time again? 4 o'clock. Yeah, I'll post the test at 4 o'clock. You should be done with your test at 7 o'clock. You need to upload it by 7:15. Okay. Okay then. See you Monday. But I still do my office hour at 3 o'clock though. If you have questions. Bye bye.
Awesome. Thank you. See you Monday.
Thank
See you
you.
Monday.
Thank you, Professor. Take care.
You're welcome.